So I just wanted to mention a couple things wrapping up this this little section on quadrics. The first is that so if we've got a general quadric like this one right here, so for some choice of signs, then I still need to tell you what happens when you have different values of A, B, and C. How do those affect it? I bet you thought I forgot, right? Yeah, well, actually I did forget, but then I remembered again, and so that's what matters. So the key fact is that this is going to stretch in the x direction, and then so on and so forth for each of the other constants that you pick. This is probably easiest to see if you look at the ellipsoids, right? So if you take A equals B equals C equals 1, then you're going to get, with all positive signs, you're going to get the unit sphere. But then if you replace, like, say, A equals 2 and then B equals C equals 1, then it's going to stretch it in the x direction, and the others will look the same. So you get an ellipse that looks like that. If you review the ellipse clip, you'll see exactly why that happens. Oh, and now my potato has shed a follicle. Go away. Okay, there we go. Terrible. Okay, never mind. And similarly for the other two. So if you're looking at, say, like a paraboloid, let's make it an elliptic paraboloid to make it feasible to draw. Then if you're missing the y variable, it's going to open up in the y direction. Suppose I've taken it to be... Oh, by missing, I mean y is the one that's not squared there. Then changing the value of A will change how rapidly it expands in this direction, and changing the value of B will change how much it expands in this direction, and then changing the value of C will change how rapidly the thing opens. Oh, I'm sorry, I said A, B, and C, but I picked one that opens in the other direction here. So this is actually C, and this one is B. There we go. Sorry about that. So if I pick like a very small value of B or something like that, I might end up with something that opens up much more slowly, like that guy, for example. Okay, so there's that loose end tied up. Also, it's worth noting that in general, the axis of rotation, or if it's not rotationally symmetric, axis of extension, so the axis sort of along which the quadric goes, is the odd man out. So if you've written it in standard form, it'll be the one with the negative sign. That will determine kind of which way the object is oriented in space. And then the last one, the last comment that I had is I just wanted to remark on the idea that if you have a hyperboloid looking function, so if you've got a function that looks like this one, say, then let's see, so the level surfaces can be superimposed on each other, right? So each one of those cases of the hyperboloids and the cones, those were all examples of level surfaces of this function here. And so if I took level surfaces which were positive, then I got a one sheet hyperboloid. If I took 0, then I got cones, and if I took negative, then I got a 2-sheeted hyperboloid. And so if we fix all these together, or not fix them together, but just sort of like stack them together, Whoops. Then it looks like this. So f is a function of three variables, right? So f is mapping R3 to R, and so it's assigning a value to every point of 3 space, and now you can see that the values assigned to these points in here are all going to be negative. Actually, that's true for, right? So for anything inside the cone, it's going to assign them negative values, and for everything outside the cones, it'll assign them positive values. So maybe this is where it's like equal to positive a half, where f is equal to positive a half everywhere on this hyperboloidal surface, something like that. And just to understand the shapes of the hyperboloids a little bit better, watch this. If we take the formula here, and if I move the -1 over to the other side so that it looks like this, then I've got, plus or minus 1, depending on which kind of hyperboloid I'm looking at. I can factor out a z squared over c squared from both terms on the right-hand side. So the first one just has a 1, and then the other one has plus or minus c squared over z squared, right? So that's just rewriting it in a funky way for no good reason, except that watch what happens now if I take the limit as z gets large. So in other words, what happens if we go up or down very far? What does it look like? Well, what happens then is that this one here goes to 0 because of the z in the denominator. So in other words, it tends toward z over c squared. So what I'm saying is that thing from the beginning is very much like z over c squared for large z. And this, if this were an equation instead of a little like wavy line approximation equation-ish thing, then we'd be looking at the equation for cones. So that's telling you then that the hyperboloids are asymptotically cones. They tend toward cones as you go up and down, which hopefully from the picture sort of looks reasonable.